All right, so we left off yesterday looking at different ways to separate out mixtures, heterogeneous mixtures, into individual parts, or like how you can use physical properties to make that happen. So one of our types of mixtures are the homogeneous mixtures, where, remember that prefix homo means what? Same or different? Good. So these are mixtures that are the same throughout, and so solutions are a special type of homogeneous mixture. And so here, I believe, no, those boxes are filled in. We're gonna get to a lot of the vocab terms today that we haven't already had. Like we're gonna, like a bunch of those S words, we're gonna try to help like have meaning to them now. Remember, your vocab quiz is gonna be next Wednesday. You will also get your study guide for the exam on Wednesday, which is a Google form, and then your exam will be on next Thursday, so a week from today, and then Friday we'll just be back to regular class. If you want your study guide early, remember, just let me know and I can email that to you, right? But you will have class time after the vocab quiz next Wednesday to do it in class. But if you wanna know ahead of time what to kind of expect, I can email it to you early, that's no problem, okay? Okay, so we're gonna look at the word solvent and solute. These are the parts of a solution. So the solvent is the substance that does the dissolving, okay? So water is typically a universal solvent. So if you think of how many things will dissolve in water, salt, sugar, Kool-Aid, right? All of those things, even like if you think of like hot chocolate, right? If you use water instead of milk, so water is a universal solvent. It does a good job of dissolving lots of different things, right? Here's how I keep the word straight. The word solvent has a V in it. The word dissolve has a V in it. So the solvent is what does the dissolving, right? So you kind of can use those little words, those letters to maybe help connect those two. Solvent does the dissolving. The solute is what actually is getting dissolved. It's the little thing that seems to disappear. I put the salt in, it seems like it disappears. I put sugar in water, it seems like it disappears. I put the powder in, and it seems like it doesn't disappear necessarily, but it's what, like you don't see powder anymore, right? It seems like it goes away or gets mixed in. Here's how I remember it. The solute, thank you, is that cute little amount. So typically, like if you're talking like you're dissolving something, you have like a glass of water, and then you put a little bit of the sugar in, or you put a little bit of the powder in. So it's the little thing. The solvent is usually the bigger amount, and then the solute is that cute little amount that gets dissolved or disappears, all right? That usually helps people kind of keep those words straight. So in a sugar water example, water is going to be the solvent, sugar is going to be the solute. So if you're looking at the picture, the solvent is the blue, the solute are these little orange sugar or salt, granules, and this entire thing is what we call the solution. So the solution, not like an answer to a problem, but it has a totally different meaning in this case, right? The solution is this homogeneous, liquidy mixture. So the solutions are made up of those two parts, the solvent and the solute. And water is a very, I always think there's another one there. Water is a very common solvent. So we'll do some practice with this. Again, we'll have a few labs that deal with this, or one lab that deals with this. But you just have to ask yourself, what's the little thing? That cute little amount is going to be the solute. And then the solvent has a V in it, and it's going to do the dissolving. And the whole thing is a solution. All right. So with solutions, there's something called solubility. And so it's the rate at which a solute will dissolve in a solvent. Some things will dissolve a lot quicker than others. Okay. And so there's some things that we can do that will increase solubility as well. All right, so solubility is basically just the ability to dissolve something. Okay, so we actually have three types of solubility or solutions, I guess. One where it's considered an unsaturated solution, where it can still hold more of that cute little amount or that solute. We have saturated solution where no more of the solute can dissolve, like it's totally full. And then supersaturated concentration, where you can do some things to try to make it hold more of the solute than you would expect it should be able to hold. All right, this always reminds me of like Goldilocks, like where she goes into the house and the one bed's too soft, the one bed's too hard, the one bed is just right, the one porridge is too hot, one's too cold, and one is just right. This is like the not enough, this is just right, and this is too much, right? In my mind, like, I don't know, like I always just hear that, that's like kind of what I always think about. So if you think about solutions or solute and solvent, so you can fit more solute, you have just the right amount of solute fitting in that liquid, and then you can convince it to hold a little bit more of the solute than you would expect it should be able to hold. Okay. When this happens, when you're at the supersaturated, it will sometimes there'll be so much solute in it that it will, like, the solute will kind of like clump on itself and it will form crystals. Those crystals will kind of they're more dense than the solution, and they can't be suspended in it anymore, and they fall out. So we call that falling out of solution if it gets so concentrated that some of that solute just kind of like starts to clump back on itself, and then it becomes, obviously it's more dense, and then it sinks to the bottom. And we'll watch a couple videos that'll show this in a minute too. So saturated contains all the solute at a given temperature. Unsaturated, well, anything that you put the prefix un in front of means what? What does un mean?
Not.
Exactly, right? So this means not saturated, right? When we put super, remember how we had superscript? What does the prefix super mean? Where was that script written when we said it was superscript for those ionic charges? Yeah, above. So this is meaning above saturation. If I said you guys are super, it means like you're above my expectations for whatever, behavior or level of work or whatever. You guys are just super. You're above what I would expect. Okay? So supersaturated means you're above what you would think would be saturation. Like you have more solute in there than you would expect. Okay? So if you think of, you know, just use those words to help you. Again, we have solution, we have solubility, we have supersaturated, unsaturated, supersaturated. It's a lot of S words to keep straight. So you have to definitely like check yourself, stop, make sure you're actually like looking and reading the word correctly, like, or like you're looking at the right thing before you go to try to answer something. Because it's easy just to be like, oh, yep, saw you, and well, okay, I was actually asking what does the dissolving, not what is being dissolved. So just take your time, make sure that you're not mixing up those S words, because it is easy to do. Okay, so here we have our unsaturated. You can keep adding more solute. Saturated means it's just right. Here you can see, and they call these little clumps of the solute crystals. And so see how they've kind of like come back, like they have clumped together, and they're kind of like stuck on each other, and then they fall out of solution and they're down here at the bottom. Because obviously they're more dense. All right, so if you think about like, think of like about like a big sponge that like you use for like cleaning or dishes or like to clean up, wipe up water. All sponges have a set amount that they can hold, right? If you have a sponge and you keep adding drips of water, drip, 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 at some point you're gonna get where that sponge can't hold a single drop more. And when that happens, you add another drop, a drop falls out. Add a drop falls out. okay? When it's at the point where it can't hold any more of that water, that's what we mean by saturation. It is saturated, it is full. Right now, our ground is probably about to be very saturated. It won't be able to hold any more of the rain that is coming down. At that point, the water starts to run off. Like, it starts to pool up, it starts to puddle, and then like if there's any kind of unevenness, it's going to find its lowest route, and it's going to start to run off and form those temporary like little streams and gullies and things in our fields and ditches and roads, right? You can all picture that? That's what saturation means. So if it's been really dry and it's raining, the ground can soak that up, right? It can soak up the rain. It can keep taking on rain more and more and more. But at some point, that ground is going to get full, and that's the saturation point. So everything pretty much has a saturation point, like where it can hold so much, that's it, no more, okay? So the same thing is true with these solutions. It can hold more and more and more of the solute until it reaches saturation, and then that's it, no more. And then you can do some things to encourage it to hold more solute, okay? And so here's some things that you can do to encourage that. You can increase the temperature. This is why, like if you make iced tea at home, usually you have to heat it up, or sometimes people you make sun tea, but they're still using the idea of having the sunlight warm the water to allow more of that tea to be able to dissolve into the water. Coffee, the same way. You have to have hot water going through that Keurig or through that coffee pot to allow that coffee to quickly be able to, or that water to quickly be able to pick up that coffee flavoring, and then, you know, basically turn the water into that coffee that you're going to drink. So temperature definitely will increase solubility. If you've ever tried to dissolve salt in water, having that warm water makes a big difference, right? Instead of just having like room temperature or cold water. So temperature definitely has a huge effect. And the reason why is actually because of motion. And this is going to kind of introduce what we're going to talk about a little bit next unit. Increasing temperature increases solubility. And actually temperature is a measure of how much molecules move. And we probably usually don't think about it like that, but thinking about what you do when you're hot. You move around, right? When you're moving around, you get warm. And so molecules are the same way. The more the molecules move around, the more the temperature of that substance is increasing. When they move around, more solute can fit in between those water molecules, and that's why it's allowing more of that solute to dissolve and like fit in to those little bonds of the water molecules. But motion is the key here. Stirring. Well, we can't heat something up. Like let's say, and tomorrow I'm going to do this, I'm going to take I'll have a beaker of water and I'll pour some of the powder in for my Crystal Light. Well, I have to stir it to make it spread evenly. Now I could also heat it, and that would allow that dissolving to happen quickly, but I'm going to just be able to stir it real quick and should be good to go. If you've ever added like Hershey syrup to milk, if you're making your own chocolate milk, you don't just put it in and then you drink it, because then you're going to get like a big drink of milk, and then you're going to get like a little spurt of the syrup. Like, you have to stir it, right? Logical. But the reason why we're stirring it is because we are basically changing the motion, allowing those molecules to spread out, and when they spread out, then that solute can like mix in evenly between the water molecules or between the milk molecules, and then it can fit in there and be dissolved. So again, increasing the motion of the solute increases the rate at which it will dissolve. Right, so I'm not sure exactly what this is, but if you just leave it in there, it's going to kind of stay looking like that. But as soon as I give it a quick stir, no problem, right? It goes right away and dissolves into that solvent. Particle size. All right, and this is again another kind of logical connection. If you have very small particles, they're going to dissolve a lot faster. So in this container, I have, I can't remember if it's 1 gram or 2 grams. I believe it's 2 grams. Each of these sugar cubes is 2 grams, and I have an equal amount of grams of sugar granules. So just my sugar powder, okay? So see, each little cube, right, each little sugar granule is a mini version of this. Same mass, right? If I put these in the same amount of water, same temperature water, which one is going to dissolve quicker? Who thinks that the cube will dissolve quicker? Who thinks that the granules? Totally common sense, right? Either that or you guys are all just geniuses. So the reason why this cube takes so long, well, the liquid, the solvent that's doing the dissolving, typically water, has 6 faces, 6 sides of this cube that it can actually work on at a time, right? There's 6 faces of this cube. Well, each one of these little granules of salt or sugar, I guess, each little cube, or each little granule is a cube. Each one of these that I'm rolling around between my fingers right now has 6 faces. Well, that's a lot more surface area that's exposed, because if each of these sugar granules, right, has 6 faces that's being exposed to the water, those granules are going to have a lot more in contact with the water, and that's why it's going to dissolve quicker. So you guys all had a good answer. You were right. They definitely do all, the granules will dissolve quicker than the cube, but that's why. It all comes down to surface area. Okay, so, and after class, you're welcome if you want to, like, feel hold the sugar cube. Has anybody ever seen sugar cubes before? They don't get used as much as they used to.
I feed them to my horses.
Yeah, so a lot of times people will feed them to their horses or animals. My grandma, like, she was very, like, traditional, and she had like this coffee set and like tea set, and she had a container that had sugar cubes. And if you've ever seen, like, on movies where they're like, do you want 1 sugar or 2? Well, and they have like little tongs and they pick the little sugar cubes up. It's an easier way, not as messy as like taking a scoop of sugar. Now, obviously, and if you watch them, then they have to like stir the coffee or tea for a long time, because it's going to take a lot longer for this cube, even though it's not as messy as using the granules. It takes a lot more time. But if you're sitting down, like having a fancy tea or coffee, like with somebody visiting or something like that, then usually you're not in a rush, so it wasn't a big deal. But that was a lot more common, you know, in previous decades than it is now. Typically we're in a rush and you just like dump the sugar in, or like have a, you know what I mean, like you're doing it quickly. But it all comes down to that surface area. Has anybody ever used like bouillon cubes for like cooking for like chicken or beef or something? The cubes, oh my gosh, they take forever to dissolve, don't they? Holy smokes. And I remember the first time, like, I went to the store and they had right next to the container with the sugar, or with the like the beef bouillon cubes, they had the exact same container, but it was like in a powder, like a granule. And I was like, it's genius, right? Because you could even heat the water and you could stir and stir and stir and stir, and then I get impatient and I like start like trying to break the cube like into pieces. The reason, like, without even thinking about it, is you're trying to make it smaller, but the reason why is because you're trying to get more surface area to be able to affect that granule, and not just, or excuse me, that cube, not just the 6 faces that are in contact with that liquid. And as soon as you're able to start breaking it, then like it starts to dissolve a lot quicker. But while it's the cube, it takes forever. So I thought that was genius that they now have a like a granule or a more powdery mix. And it's like 1 teaspoon to every sugar cube, like, so you can use the same equivalency or whatever. But today I always make a big mess up here. So those are the things that will affect solubility. So if you can heat something or stir it, a lot of times you're going to be able to increase the solubility and make something that is saturated become super saturated. Typically you're not going to be able, like, if you just keep adding sugar, it's just going to fall out. Like, it's not going to be able to be held in that solvent. It's not being dissolved. It can't hold it anymore, and it just falls out. And eventually it can even form those crystals if you put too much. So we can try to affect the solubility by doing these things to it, but at some point it's still gonna become like, that's it, like it can't take anymore. Right, and so it all comes down to the idea of surface area. All right, so temperature definitely allows more solute to dissolve. That's why you heat the water to put that beef bouillon cube or chicken bouillon cube in. That's also why, you know, a lot of times you besides having coffee that you want to have hot, a lot of times, you know, you do it so that it dissolves the coffee grounds easier and better. So temperature is directly related to kinetic energy, and this is going to be a big part for next unit. Kinetic energy is the energy of motion. So as temperature goes up, kinetic energy or motion of these molecules goes up as well. And so the more kinetic energy, which we're giving the abbreviation KE, the more the molecules are moving around. And the more they're moving around, the more space there ends up being between the molecules. There's more space between the molecules, then that solute can just slide right up in there, right? And fit more of that solute into the solvent. So it allows more solute to fit into the open space. When molecules are really tightly packed, that is a very low temperature usually. And so if things are tightly packed, you can't fit that solute in there. Like there's no room for it to fit. So this is kind of interesting for this time of year. If you add solute, it actually lowers the freezing point, making it harder for something to freeze. That solute kind of interferes with the bonds coming together to form the solid. And so you can see, like, if this is getting colder and these molecules are coming together, molecules coming together and packing in tight, that's what makes something a solid. And so, and again, we're gonna have this whole big unit on this next unit with states of matter. But as things get colder, they come packed together. Those molecules pack in tight. Well, if you put, let's say, salt as a solute and disrupt that, some of that salt will get in there and it keeps those water molecules from going from the liquid to the solid. And so this is what they use, or this is why they use salt on our roads. Those solute particles can interfere with the crystals forming and keep that freezing process from happening, which is great for our roads. So that, and I know, I think it was last Thursday, Friday maybe, they sprayed the roads, they put like the treatment on the road. And the reason they were doing that is because they knew that the temperatures were gonna fall and we were supposed to get some rain, and they wanted to keep it from freezing on the road. And so that, they know that it keeps it, the water molecule bonds from going from a liquid to a solid. That salt gets in there and interferes with that crystal formation, and then it doesn't get to form the ice, which is more dangerous, obviously. So we take what we know in science and apply it to real life, and that is very helpful. Okay, so you're not going to have to graph things, but there are ways that you can see something's solubility on a graph. So you can read, you can do some comparisons. So the first thing we always do is look at our axis label. So we have temperature in degrees Celsius, we have solubility, and it's grams of solute per 100 grams of water. So how many grams can dissolve at a set temperature? That's basically what this is about. Has a nice title, solubility curve for potassium nitrite. So I have this line. This line specifically shows the saturation. So as temperature increases, you can see I'm able to add more and more and more and more grams. Okay? There's a very set point. So like at 90 grams, or that would be at 50 degrees Celsius, I could dissolve 90 grams in that water. At 70 degrees Celsius, I could dissolve 140 grams. So I can't get 140 grams to dissolve if I'm only at 50 degrees. right? I would need to increase my temperature up to 70 degrees Celsius before I could fit that extra amount of grams into that solution. But by increasing the temperature, you're allowing more room for that solute to kind of fit. And that's what this graph is trying to show. So here's some ways that the questions could be asked. I could say, you know, where is saturation? Well, it's anywhere along this green line, okay? Notice how underneath the line, it says unsaturated, okay? Un means not. In this example, you could also think, okay, it also means under, un and under. Anything under this line is our unsaturated. Anything above the line, we're going to call that the supersaturated. So you have this line, think of shading this in, that would be considered supersaturated. Right, let me do this real quick. Have that. We'll see it on another one. So if I give you a point of 30 grams at 40 degrees Celsius, I might ask you, if I have, oh gosh, that's bored. That's weird. So if I have a point right there, I would say, okay, is this saturated, supersaturated, or unsaturated? Under this green line, it would be unsaturated. If I put it right on the green line, that would be considered saturated. If I have like at 110 and 20 degrees Celsius, then I would know that it is considered supersaturated at that point. So when you have multiple lines, make sure that you're looking at the right line or else it's gonna mess you up, obviously. So actually I am gonna switch my settings real quick. I forgot I needed to draw today. Yeah, I have to do it over here. So this is going to give you the example, or show you some examples of how these type of questions could be asked. There we go. Should be good now. Yes. All right. So it says 100 grams of solute dissolves in 57 degrees Celsius. What was used? So I'm just going to find these, and then I'm going to see which one of these lines it puts me at. So if I find 100 grams, so I always look solubility of grams over here, and I have temperature in degrees Celsius, and these are all showing solubilities of different solutions. So I'm going to find 100 grams. So if I'm at 100 grams, oops, right, I'm looking right around here, and then it says 57 degrees Celsius, so I'm at 45 to 50, so I'm going to be kind of like in the middle of that.
No, it goes by 5s on that one.
Yeah, 45 to 50.
It's 57, so it should be between 55
Oh,
and
57,
60.
jeez Louise. Yeah, sorry. I'm going to fix my calibration, because I was looking at my lines being off and just talking crazy. Thank you. Sorry. This will be better. Okay. All right, so let's go to 57. 55 to 60, so I'm going to be just beyond, yeah, that's better. Just beyond my 55, and so look at that. It puts me right there on this line, which is saying is potassium nitrite. Okay. So you just have to follow basically the coordinates, right? And so I know that's potassium nitrate. Now, Ki is potassium iodine. So if I would happen to give you the chemical formula and you're like, what? Which one of those lines is it? Just ask me. But that should be potassium iodine. So I know I'm going to be looking at this line. All right. So I want to key in on that and make sure I'm looking at the right line before I even start to answer anything. Oops. Wow. We'll make sure that's right. How many grams of the Ki were used if it dissolved at 15 degrees Celsius? So I'm given the 15 degrees Celsius. So from there, I'm going to put my finger on it. I'm going to go all the way up, right? And I'm going to keep going up until I get here. So that puts me, right about here. And then from there, I want to know how many grams. So I just go over to my y-axis, my dependent variable, and I say, okay, it looks like it's above 150, not, halfway. So, probably like maybe 155-ish. Maybe that's a little low. But you'd have to be between 150 and 160 at least. So these are usually going to be kind of an average or an estimate. So this is just using a graph, right? It's nothing too extreme or intense. It's just making sure you're actually looking at the correct line, making sure that you understand that temperatures are down here. And if it's asking for grams, then you're going to go from the temperature, hit your line, and go to your grams. This one is asking what kind of a solution is found at 75 degrees Celsius for 70 grams of potassium chlorate. So here's my potassium chlorate. So I'm going to make sure I'm looking at the correct line. And then from there, I'm going to go to 75 degrees Celsius. Right, so it puts me here and 70 grams. So 70 grams and 75 meet like right there. Well, if I'm looking at this blue line, this is all above. If I'm above, which type of solution is that? Is that saturated, unsaturated, or supersaturated? If I'm above this line, Garrett? It's going to be super. Good. So sometimes these graphs have a lot going on, but just kind of key in and focus on what specifically, which line you're looking at, what is it asking, what's it giving you, and that kind of thing. This, let me get rid of my mess. This is kind of a nice visual. This line right here, that is the only place where it's exactly saturated. So it's like just right? And anything under that, and look, you can see these little white dots are the solute. It looks like you can fit a lot more of them, right? So unsaturated, this visually shows you, yeah, I can fit more. Supersaturated, anything above the line, ugh, that looks really packed, doesn't it? Doesn't look like I could fit a whole lot more of anything in there. It is already above, like it's already holding more than it should or what you would expect it should be able to hold. Okay, is that the last one?
Yeah.
Whew. All right. We probably won't be able to finish it, but I want to hear it because it's been a while and it's one of my favorite of his songs.
This love song?
No, but it's Mr. Edmonds, but it's a good one.
Better.
You'll recognize the song right from the get-go.
I know.
Wow.
A solution is a type of mixture that is homogeneous. It means that it's the same throughout, the same throughout. It is the best mixed mixture of two or more substances. When one of the components is water, it's aqueous. The major portion of the solution, the thing that does the dissolving, it bears a special name for its job. It's called the solvent. The other part of the solution, the thing that gets dissolved, it also bears a special name. It's the solute. Solutions are made of the solute and the solvent. The solvent, it does the dissolving. The solute is lesser. It's the substance that gets dissolved. Solutions, the best mixed mixture.